Welcome to the Explainer. So if you're using Docker, you already know it's an absolutely incredible tool for modern development. But today, we're going to look at it through a slightly different lens. We're going to treat Docker containers not just as, lines of code or isolated processes, but almost like living, breathing organisms. By tracking their birth, their active life, and their eventual retirement, we're going to help you completely master the command line interface ecosystem.
We've got a great roadmap for this journey today. We'll be hitting 5 key stages: demystifying the Docker CLI, the core container lifecycle, blueprints and managing Docker images, networks and persistent volumes, and finally, system cleanup and maintenance. Our goal here isn't just to memorize commands, it's to really understand the actual logical lifecycle of a container.
All right, Section 1, demystifying the Docker CLI. Let's get a really solid grip on what we're working with before we even touch the command line.
Okay, so the crucial point to remember is that Docker allows us to create these perfectly isolated temporary environments that run consistently absolutely anywhere. Whether you're on a Mac, a Windows machine, or a Linux server, Docker packages your software with every single one of its dependencies, so it behaves exactly the same way. It uses OS-level virtualization to keep these environments incredibly lightweight, and that's a huge deal because it means you can run multiple isolated containers on a single host without all that massive overhead you'd get from traditional virtual machines.
Just to ease you in, here are the everyday foundational commands you'll be using to interact with your active containers. You've got Docker PS to see what's currently alive and kicking, Docker run with the detached D flag to spin something up in the background, and Docker stop to, politely ask a container to halt its processes. Honestly, these 3 commands make up the absolute foundation of your daily workflow.
And this is exactly why learning the CLI is so insanely powerful. I mean, if you read through the recent Docker desktop release notes, you'll see a constant stream of fixes for the graphical interface. Things like fixing WSL integration permission denials on Windows, or resolving hanging resource saver modes, or UI thread deadlocks. The desktop app is fantastic, don't get me wrong, but by mastering the command line, you get complete, uninterrupted control regardless of whatever weird bugs or tweaks are happening in the GUI. The CLI is your absolute source of truth.
Moving right along to Section 2, the core container lifecycle. Let's dive into how a container actually lives, breathes, and retires.
The best mental model for a container's life story is this very specific chronological sequence. First, you pull the image from a registry, like Docker Hub. Second, you run it, bringing it to life. Third, you inspect its vital signs using commands like Docker PS. Fourth, when its job is completely done, you stop it. And finally, you remove it entirely to clear up your file system. Once you understand this flow, you'll always know exactly where a container is in its lifespan. Now, the real magic happens when we look at the difference between running a container in the restrictive foreground versus the freeing, detached background mode. By default, when you use Docker Run, that container runs in the foreground. It attaches itself to your standard input and output, literally hijacking and blocking your terminal until the container stops. But simply add the D flag and you start the container in detached mode. It goes about its business in the background and immediately hands your terminal back to you so you can keep on working. Total game changer.
Of course, during its active life, a container needs to actually interact with the world. It can communicate with your host machine via port mapping. Using -p 8080/80 takes port 80 from inside the container and exposes it right to port 8080 on your machine, which lets you actually access the web app running inside. Or, if you need to, say perform some surgery or just poke around, you can literally step inside a running container. Using Docker exec with the interactive -it flags and passing /bin/bash opens up a shell directly inside that living container. So all of this naturally brings up a critical question. Where do these living containers actually come from in the first place? If they're living organisms, what dictates how they're built? Well, that leads us straight to their foundational DNA. Let's get into Section 3, Blueprints, Managing Docker Images. Because every living thing needs DNA, and in the Docker ecosystem, those blueprints are called images.
Basically, an image is a super lightweight, standalone executable package. It includes everything you need to run a piece of software: your code, runtime, system tools, libraries, the whole shebang. You build these packages directly from your own custom instructions in a file simply named Dockerfile. When you run docker build tat followed by a name, you are compiling that text file into a reusable blueprint and tagging it with a specific name so you can easily spawn brand new containers from it later.
But here's the catch. As you constantly tweak your Docker files and rebuild those blueprints, you are inevitably going to create what are known as dangling images. See, if you rebuild an image using the exact same name, Docker strips the name and tag from the old version and replaces them with none. These dangling images are essentially unused digital ghosts haunting your hard drive. They aren't doing any harm, but they are absolutely useless clutter, eating up precious space.
All right, so we know how they're born, and we know they can be stopped and removed. But before we get to the system cleanup phase, we have to solve a bit of a mystery. Where does the important data go when a container dies? Like, if a database container is removed, does all its data just vanish into thin air?
Let's answer that in Section 4, Networks and Persistent Volumes. We'll explore how containers communicate and how they carry their data in external backpacks to ensure it survives.
So by default, a container's file system is totally ephemeral. When the container is deleted, the data inside its writable layer is gone forever. Poof! But by creating and mounting volumes using the V flag, you're basically handing the container an external hard drive. Volumes act as persistent directories that are managed by Docker, and they're stored safely outside the container's temporary file system. This guarantees that your crucial application data, like a database's customer records, survives long after the container itself has been destroyed.
Now, there is another way to mount data, and it's called a bind mount. You gotta be a bit careful with bind mounts, though. Unlike a standard volume, which is managed safely in an isolated Docker directory, a bind mount takes a highly specific path from your actual host machine, like your desktop or your documents folder, and literally forces it into the container. It directly overrides the container's internal path with whatever is sitting on your host machine. It is fantastic for local development, letting you edit code on your machine and seeing it update live in the container, but it heavily ties that container to your specific host's file structure.
And just like real living organisms, containers usually don't do so well in total isolation. They need to talk to each other. This is easily handled by creating networks they can connect to the second they start up. Using Docker Network Create, you can establish completely isolated networks. Usually a bridge network if you're on a single host machine, or an overlay network if you're dealing with a whole swarm of machines. Once containers are attached to the same network, they can seamlessly chat with each other by name, which perfectly mimics a secure internal internet just for them. All right, we have made it to the final stage of our journey, Section 5, System Cleanup and Maintenance, because maintaining a healthy environment is honestly just as important as building it.
When your system inevitably becomes cluttered with the ghosts of containers past, the Docker System Prune command is absolutely your best friend. It acts as this highly efficient digital janitor. With one single command, it obliterates all stopped containers, any networks that aren't actively being used, all of those dangling none images we talked about, and all leftover build cache. Making a habit of running this regularly is the key to keeping your performance high and getting gigabytes of hard drive space back.
But a quick word of warning. Before you start aggressively pruning everything in sight, you should always check the vitals of your environment. You can check the live pulse of your running containers using Docker Stats. This streams a live readout of CPU and memory utilization, which is perfect for spotting any performance bottlenecks. And if you need to zoom out and see your entire configuration, like how many containers and images you actually have, your storage drivers, and deeper system details, just run Docker Info. It gives you the total situational awareness you need to manage your ecosystem safely.
So, we've taken containers from their image DNA right through their active running lives, mapped out their external networks and volumes, and finally cleaned up their digital footprint. Knowing that you now have complete bulletproof control over this entire container lifecycle straight from the command line, the only question left to ask yourself is, what are you going to build and containerize next? Thanks for joining me on this explainer, and happy building.